So we've seen that before, negative and positive relations. So why are we introducing an actual number for these relations rather than just relying on strong, weak, moderate correlations? Well, the reason that we're introducing this Pearson R number here is because when you're talking about strength of a relationship, you cannot help but bring into that judgment your own personal biases. And by figuring out a way to assign a number to it, we can remove those personal biases from the equation. So what I mean by that is, let's say that you collected this data and you are a strong proponent of exercise and its effect on mood. And you're giving a talk and you put this data up there and you say, look, we collected how much people exercised and we also gave them a mood scale. And as it turns out, the more exercise you have, the higher the mood. There's a positive relation here. And I believe this is a really strong relation. The two of them are strongly correlated. This is a strong relationship between the two variables. And a hand goes up in the back of the room, and this person has a personal agenda against exercise. They're anti-exercise. And they put up their hand and they go, you know what, I'm looking at your data and it looks like a weak relation to me, right? Those points aren't too tight. That's kind of a weak relation. And you'd be standing there going, no, look, they're very close, strong relation. And they would be saying, no, look how spread out they are, weak relation. And you could go back and forth like that, and nobody's gonna convince anybody else. So we can't rely on our own human sort of interpretation of these. We need to outsource it. We need to make it objective. We need a procedure that can assign a number that everybody can agree on. Because when somebody says, this is a positive correlation, and the correlation coefficient is 0.7, nobody can put up their hand and say, I don't think it's 0.7, that looks like a 0.5 to me. Because it's math, it's statistics, it's a number, it's something everybody can agree on. So that's where we get this Pearson correlation coefficient. It is the statistic that measures the strength of these correlations. It can go anywhere from 0 to plus or minus 1. So it can go all the way from -1 to 0 to +1. And it has those two components. One is the sign, one is the strength. So the sign here tells you whether it's a positive relationship or a negative relationship. And then the number from 0 to 1 tells you how strong that relationship is. 0 is a completely weak relationship, no relationship. 1 is that perfect relationship. And depending where you are on the continuum, you'll be somewhere in between 0 and 1. So let's take a look at the R for positive relations. So in this case, we have no relation. There's your line to show that there is no relationship between exercise and mood. And if we were to calculate a correlation coefficient for this, correlation coefficient would be plus 0.02. Very close to 0, positive, but very close to 0, indicating an extremely weak correlation. If we increase the strength of the correlation, so now knowing something about exercise will predict something about mood, you can see that our correlation coefficient has gone up. It is now 0.23. And if we increase the strength of our relation once again, correlation coefficient has gone up corresponding to that. So now it's at 0.51. So if we get to that one that we thought was a strong relation, we find out that the correlation coefficient is 0.77. And nobody can argue with 0.77. You could argue all day about whether this is strong or weak when you're looking at it. But when you say, oh yeah, I've calculated the correlation coefficient between exercise and mood, and it's 0.77, even the anti-exercise person in the back is going to have to say, all right, it's 0.77. And your perfect relation, the absolute pinnacle of how related two variables can be, that has a correlation coefficient of 1. That's the upper limit. Can't go higher than 1. 1 is a perfect correlation. So that's a correlation coefficient for positive. You can also have correlation coefficients for negative relations. And for the negative relations, it's important to remember that correlation coefficients come in two components. One is the sign, one is the strength. So when you have a weak negative correlation, you'll have that negative sign. That indicates that it's negative. And then once again, the number indicates how strong it is. So one of the mistakes that people oftentimes make when they're learning about correlation coefficients is thinking that a minus 0.23 correlation is somehow weaker than a positive 0.05 correlation. The truth is the opposite. 0.23 is stronger than 0.05. Negative just indicates the direction. So make sure that you keep those separate. This minus doesn't mean that this is low. What it means is that it's in the negative direction, and then the 0.23 indicates that it's strong. It's just now strong in a negative direction. Make that relationship even stronger. Notice the number gets even more negative, closer to -1. And once again, that 0.51 indicates the strength. The negative indicates the direction. We increase the strength once again. We see that the correlation coefficient has now gotten even stronger. And then finally, perfect correlation. You'll never find it, but it leads to the maximum correlation coefficient, in this case, -1. Minus for negative relation, 1 for the strongest relationship possible. All right, any questions so far? Okay, so before we get into interpreting these correlation coefficients, one last thing I want to point out is a little bit of math magic that you are going to encounter, because people use correlation coefficients a lot. That's one of the reasons I wanted to cover it. But this has to do with effect size. Now, effect size is a term for the general strength between two variables. And what statistics has done is it's made a whole bunch of measures for the strength between variables in certain situations. So for example, if you have two variables and they're measured on ordinal or interval scales, you can calculate a correlation coefficient, and that will give you the strength of the relationship between these two. Effect size is a general measure of the strength of the relationship. So it's a way of comparing relationships across different measures. So if you have like a Pearson correlation coefficient, and then somebody else runs an ANOVA, and then somebody else does a regression analysis, you can come up with effect sizes that will allow you to compare across those three different tests. It just so happens that somehow the effect size when you're doing correlations is calculated by just squaring the correlation. So the percent, and what this is, it's the percent of variance in one variable that is accounted for by the second variable. And that's a phrase you'll see as you continue to move through psychology. The percent of one variable that's accounted for by the other variable, the percent of variance that's accounted for by the second variable. And it just seems magical that if you square this number, you can get that percent. And because this is squared, it's going to go anywhere from 0, so 0 squared is 0, all the way up to +1 only, and that's because +1 squared is +1, -1 squared is +1. So all the negative correlations, when you square them to get their effect size, they're going to turn into these positive percentages. So what does this look like? What does this mean? Well, again, it's that idea, we've kind of seen this before, it's the idea of you have a certain amount of variability, and how much is knowing about one variable going to tell you about the scores on that other variable. That's what that reduction in variance is all about. And if you have a very weak, almost non-existent relationship between your variables, if we square that, we can see that knowing about exercise will be able to reduce this uncertainty by 0.04%, not even a full percent. So if somebody tells you how much an individual exercises, that's not going to tell you anything about how much, what their mood is like. In fact, it's only going to reduce it by 0.4%. So if you knew that somebody was had a low level of exercise, rather than having to guess between these two red lines, you could reduce your uncertainty and only guess in that green box. If you knew that somebody had a middle amount of exercise, instead of guessing between these two red lines, you could reduce that by a whole 0.04%. Right? So it's not helping you at all. It's reducing none of the uncertainty. as the relationship between the variable strengths, as the strength of the relationship increases, the amount of uncertainty increases as well that you can reduce. That reduction in uncertainty is increased. So if you have a correlation of 0.23, that gives us an effect size of about 5%. And what that means is that if you know the exercise amount, instead of having to deal with 100% of the uncertainty, you now only have to deal with 95% of the uncertainty. So it's told you a little bit. Knowing about exercise tells you a little bit about mood. Knowing about exercise takes the 100% of the uncertainty about mood and reduces 5% of it. So it's helpful, not very helpful. And the higher your effect size, the stronger your correlation, the more reduction in uncertainty you can get. So for this relationship here, slightly stronger with a correlation coefficient of 0.51, you square that, you get 26%. Knowing about exercise right now will reduce this uncertainty from 100% down to 74%. It'll take 26% of the uncertainty away when you know about exercise. So again, if you're trying to guess what the mood is and you have no information, 100% uncertainty. As soon as you know what the exercise level is, only 74% uncertainty, because you reduced uncertainty by 26%. And that's going to be for whatever amount of exercise you know, it'll reduce that uncertainty. Yep.
So the effect size is the 26%?
Yes. It's the 26%.
Okay.
And what was, so the 74% is how much uncertainty is left. The effect size is how much has it been reduced. All right, and so on and so forth. If we have a 77 correlation coefficient here, that leads to a 59% reduction in uncertainty, which means that telling you about the exercise will be able to reduce that uncertainty by 59%. So you're only dealing with a 41% window when you're trying to guess what that level of mood might be. And in the extreme example here, if you have a correlation coefficient of 1, you have an effect size of 100%. And in this case, if somebody tells you the amount of exercise that a person has, you can reduce the uncertainty in what their mood is by 100%. So with no information, if somebody said, what's the mood of a particular individual? You'd be like, I don't know, anywhere from down here all the way to up here. It could be anywhere in there. I have 100% uncertainty. If they then tell you, oh, well, they exercise two hours a week, you can say, oh, well, in that case, their mood is exactly right there. They got 50, score of 50 on the mood index. If they say, oh, no, they actually exercise 6 hours a week, you'd be like, oh, okay, exactly 60 on the mood index, and so on and so forth for any levels of exercise. So that would be the ultimate amount where you can predict one exactly. So again, the only examples where this ever occurs are on things like where one measure is converted into another measure directly. So if I was to say, what do you think the height is of Dr. Ladd? What's the height in inches of Dr. Ladd? And you're like, I have no idea. Give me some information. And if I said, well, he's 176 centimeters, well, you can perfectly predict how many inches he is because you just Google it on your phone and do the conversion. That's the only time this ever really happens. But this is kind of like the ultimate holy grail of what you're trying to attain. All right.